Good afternoon, and welcome to today's Electronic Design Webcast. Our topic today, HighSpeed Fuseology, sponsored by PTI and Littelfuse. I'm Bill Wong, Senior Content Director with Endeavor's Design Engineering Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. This webinar interface allows you to resize the presentation by clicking on the maximize icon or by dragging the lower right corner to enlarge the window. Additionally, we welcome your question during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speakers. Brandon Blume has 5 years experience in the electrical industry. He has worked at the distributor and manufacturer level in the industry, primarily at the OEM customer base. Ray Zumbahlen has worked at Littelfuse for 9 years and has been involved in various engineering functions focusing on industrial fuse validation, design, and application. You can learn more about our speakers by clicking on the blue speaker bio widget on your console toolbar. Now let me turn things over to our presenters. Gentlemen, the floor is yours.
Thank you. So, as they mentioned today, the training will be over high-speed fuses and several factors that are associated with picking high-speed fuses. An important part of that we'll talk about today is when you're looking at a system that you're trying to protect is understanding the needs for an overcurrent protected device and how that affects the overall protection for the system. Some things we hope that you will take away after this training is first, the benefits of high-speed fuses and why they are necessary. Second is to overcome common challenges, which we'll discuss, of protecting power semiconductor devices, which these fuses are used for. Third is identifying which fuse characteristics have an impact on device performance. Some have a heavier effect and some can be minimal. Last, we'll discuss how to fuse implement robust protection to ensure a reliable system, which is the end goal here. So first, let's discuss semiconductors, which are the main devices that these fuses are used for in terms of application and function. So there are two common types of semiconductor devices that would break into 2-terminal devices and 3-terminal devices. Most common that we see or come across when we're looking for high-speed fuses and applications are IGBTs, which is the insulated gate bipolar transistor, and also MOSFETs. How these power semiconductor devices tie in are in terms of modules. They combine in terms of components to form the overall system in terms of how they tie into the products and the application. Most of the times, you'll take many of these smaller components and combine them to protect something, and then however this device needs protection. Why they do need protected is because, in general, power semiconductor devices are very sensitive and they're susceptible to 2 types of failures. They combine high power handling and fast switching capability in a small package size. With that, these devices generate excessive heat during their normal operation and have low thermal withstand capacity. Additionally, any reduction in size impacts the device's ability to withstand overcurrent and overvoltage. This causes the device to require additional arrangements such as a heat sink and or forced air, liquid cooling to dissipate the heat and help them run cool. To prevent against this, we need a protective circuit device. The fastest available in the market is the high-speed fuse. High-speed fuses have proven to be the protection devices that offer the proper level of protection to these sensitive power semiconductor devices. Types of failures for these devices would be a thermal overstress, which would have to do with oxidation or cooling component failure, and other is electrical overstress, so transients and insulation failure. On the right is some images that show in terms of a case rupture during an explosion or during a short over these devices. So when we look at high-speed fuses and where we use them, we want to first ask, now that we understand the need for them, where can we use them and what are the typical applications? The most common that we see are inverters, process industries, and drives and starters. And the second kind of category would be solar, power generators, UPSs, and heaters and welders. And last would be EV chargers and energy storage systems, which is a very fast and growing market right now. If you had to take those applications and kind of group them into a whole overview category, first would be industrial systems. So we have industrial, and then we'll get into the second category after this. But industrial motor systems or industrial systems would break down into three more specific. So first would be industrial motor drives. So that would be variable frequency drives, inverters, UPSs, and high power stack assemblies. How this is different is the fuses are used internal to the device in terms of maybe protection inside, protecting some of the devices inside the drive or the power supply. Second would be motor control centers and panels, so large industrial panels, replacement, process industries, and things like that. If you see the fuses on the categories, those are how we have aligned where our fuses, our products are. We have different types of high-speed fuses, which we'll get into, and how each of these products would tie into, or which product would tie into these applications. Third would be auxiliary equipment. So a little bit smaller type of equipment, crane, hoist panels, testing equipment, maybe some motor generators, exciters. These would be a little bit shorter design cycle, as in it's a smaller device, it's not as much design time and spec work in terms of what product they're designing or making. The second category we group these in would be commercial and alternative energy. So that would be into solar inverters and UPSs, so central inverters for DC array combiners or a power converter, and also UPSs, so DC to DC converters and DC to AC converters. They can be used on the input and the output side, depending on the system design. Second is battery energy storage systems. So becoming more and more popular in the utility world and the commercial world for energy storage, taking battery racks and storing energy for the grid or for emergency purposes. So high-speed fuses are used very often for that, and also in inverters. So for solar inverters or just inverters in general, converting DC to AC or power generation. Last would be the DC fast charging stations. So the level 3 charging stations, the larger ones that you may see for super fast charging, would normally see larger high-speed fuses used on those for the converting on the power and also on the DC cable. So next we'll talk about overcurrent protection fundamentals, which have to do with some key technical details about high-speed fuses and how we break that down in terms of a definition standpoint. So if you're looking at a high-speed fuse and its classification, how is that different than any other fuse? The high-speed fuses are classified based on the protection level offered. So per UL 248 and IEC 60269-4, it's a standard that classifies based on utilization categories. So if you look on the right-hand side of the picture, it breaks out into the two letters. So the first letter would be for range of operation, and the second letter would be the application that it's protected for. So in terms of high-speed fuses, there are two types of range of operation. The first would be a partial range fuse, which would be a lowercase a, and the second would be a full range fuse, which would be a lowercase g. The first letter denotes the range of operation. Like I said, with the partial range, it would only be for short circuit protection. So for very high current at a short amount of time, this was what this type of fuse would be used for. However, on the other case, a lowercase g, a full range fuse, would be used for both short circuit and time delay protection, enabling that fuse to pick up current at a much quicker time and activate. And the second letter, which is a capital R, denotes that it's a semiconductor device protection, which means, for a high-speed fuse or for this type of, this is the application that's protecting for. That could be different depending on if it's a UL fuse or, a traditional fuse. So if we take that fuse and we look at, how that fuse is different in the internals and also just on the information provided. This is a cutaway of we call a square body high-speed fuse, which is our fastest fuse. And the different components help that fuse to be as fast as possible, breaking down from the pure silver element bridges and the stone sand for faster quenching of arches, and also the ceramic body that has to do with heat dissipation. If you look at the label on the right-hand side, it will break down in terms of different ratings and approvals and things that are needed for customers for their application or what they're designing for, which we'll get into. Why would they want a fuse to be rated for a certain ratings, whether that be for current or voltage. So when we take those fuses and we look at, how does a square body compare to a round body? If you're looking at the different components, it depends on the application and what type of protection the customer is looking for, whether that be they need a faster, a higher rated fuse, or they need something just to be in there for in case of a short circuit, like a very high current coming through. So in terms of the round body and the square body, these are the differences. Some of the same components. However, the square body, like I said, is a faster fuse just because of what we designed this fuse for in terms of higher current DC voltage as well. However, most of the components are very similar to a round body fuse. So if we're looking at a high-speed fuse and we're seeing how it operates, how does this fuse operate to be able to protect a semiconductor device? So inside the high-speed fuse, there is, an element that we call, and during that element there is operating conditions or stages that element will go through when that fuse is enacted and designed to react. The first, these elements are designed to carry a specific amount of a current based on the fuse rating. Say if it's a 600 amp fuse, it's designed to carry that a specific amount of current continuously without opening. And that's referred to, like I said, the rated current of the fuse. During those operations, it will start with the normal operating condition and pre-arcing, and then operated once the fuse will discontinue the current through the system and then operate as a fuse, which it should. So to put that in a graphical standpoint, we'll look at the basic functions of current and voltage inside of a fuse. With an overcurrent is any current larger than what the equipment, conductor, or device is rated for. during under specified conditions. Unless it's removed in time, even moderate overcurrents can quickly overheat system components, which in turn can damage insulation, conductors, and equipment. There are two types of overcurrent. The first would be overload, which is less than 6 times the rated current. And the second is a short circuit, which is greater than 6 times the rated current. When there's an imbalance in heat transfer due to overcurrent, a rise in temperature at the fusible element's restrictions or weak points causes this fuse to start to operate and react. When this rise reaches the melting point of the element material, the element bridges begin to melt and separate, resulting in, like I said before, interruption of current flow through the fuse. And this graph just shows, how the peak current is occurring with the fuse and how that fuse is helping the clearing time. With that being said, I'll turn it over to Ray, and he will talk about performance characteristics. Thank you.
Thank you, Brandon. So let's start off with talking a little more detail about high-speed fuse characteristics. High-speed fuses typically have additional published data and highly detailed data sheets when compared to general-purpose industrial fuses. Their data sheets include many characteristic curves that represent a fuse's electrical performance capability and show how 2 electrical parameters may correlate. So some of the key performance characteristics that we want to cover are shown here in this snapshot. These 6 curves are the most commonly used by individuals that perform high-speed fuse selection. So the first curve to discuss is the time current curve, or TCC as many people call it. A TCC represents the inverse relationship of time and current for fuses, illustrating how the pre-arcing or melting time of a fuse decreases with an increase in prospective symmetrical overcurrent. It is generated based on standard test conditions and at an ambient temperature range of 20 to 25 C. A TCC can be used to determine a fuse's pre-arcing time for a given symmetrical current, which may be necessary to select the proper fuse current rating for an application. The x-axis of a TCC represents the symmetrical RMS fault current in amps, and the y-axis represents the pre-arcing time for the fuse. This is the time duration from the initiation of an overcurrent condition to the instant that arcing begins inside the fuse. So to determine the melting time for a fuse, start by locating the prospective symmetrical current on the x-axis, which you can see as point A on the left curve. Then extend a line from point A upward until it intersects with the fuse TC curve at point B. Finally, move to the left to identify the corresponding value on the y-axis at point C, which represents the fuse's pre-arcing or melting time. The chart on the right shows a typical example of a partial range high-speed fuse, TCC, that has solid and dotted line regions. The symmetrical overcurrents for which high-speed fuse offers protection is identified by a solid line. Overcurrents outside of the fuse protection limits are represented by a dotted line on the TCC, which typically exists at the low overload fault levels. The intersection of the solid and dotted lines represents the rated minimum breaking capacity for the fuse. That is the minimum level of overcurrent the fuse can be expected to safely operate and open the circuit. The shaded zone identified at the top of the figure on the right represents the unsafe operating region for the fuse, which correlates to the dotted line region. Any combination of RMS current and time that falls within this region will put too much thermal stress on the fuse, which could result in a catastrophic failure. While selecting high-speed fuses for applications with varying load currents, care should be taken such that the fuse should not be subjected to a load current for an amount of time that falls into the unsafe operating region of the fuse selected. So now let's go over a few quick TCC scenarios. So here's an example, I guess. What is the operating time for an available fault current of 1800 amps. So this TCC curve shown is the same on the left and right for a 200 amp fuse. So when this 200 amp fuse is subjected to a fault current of 1800 amps, you can identify the melting time that you would expect for that fuse. So this is what we discussed earlier. So on the fuse on the left, locate 1800 amps on the x-axis at point A, move up to point B at the intersection of the curve, move left to the y-axis, and it's certainly hard to see here on this curve, but the point C is actually at 0.002 or 2 milliseconds. So that said, when that 200 amp fuse is subjected to a fault current of 1800 amps, which is 9 times its rated current, it will melt within 2 milliseconds. So next scenario here, let's see if this fuse can withstand a momentary overload of 400 amps for 5 seconds. You can see that is actually noted by the upper red dot, and the answer would be no here. That red dot lies within the unsafe operating region. And let's locate the point for a momentary overload of 700 amps for 1 second. That is the lower red dot, and it is not located in the unsafe operating region, and it is to the left of the TCC curve. So the answer would be yes. That would be an acceptable condition for this 200 amp fuse to see 700 amps for 1 second. The fuse would not melt. Let's move on to the next curve, which is the peak let-through curve. So let's start with a bit of background information on this. High-speed fuses are extremely current limiting. It's one of the many benefits of using high-speed fuses. A current limiting fuse will begin to limit the current and energy let through the circuit when it is subjected to a high enough overcurrent that results in clearing times of less than 10 milliseconds. The image on the left is a graphical representation of this condition. With no fuse in the circuit, the energy let through on a short circuit event is the sum of the light and dark green areas as well as the gray area. With a current limiting fuse in the circuit, the amount of energy let through this system is the sum of the light and dark green areas only. So in this case, the fuse being in the circuit would decrease the peak current and limit the total amount of energy let through the circuit. So that is just a representation of the condition. The actual peak let-through curve that you can find on a data sheet can be seen on the right. It actually is what gets published and can be used by a customer to determine just how much the available peak current will be decreased and actually let through the system. So on this curve, the x-axis represents the available RMS fault current level, and the y-axis represents the available peak fault current level. The gray line depicts the relationship of RMS to peak current for circuits with a 15% power factor. And the green line represents the limited let-through current for various fuse ratings. Let's walk through a quick example for this using this curve. So what is the peak let-through current of a 600 amp fuse at a short circuit fault of 100 Ka? So the fuse rating is 600 amps, fault current 100 Ka. So at point A1, we find point A1 at 100 Ka on the x-axis. We move up until we intersect the green line for the fuse that we are interested in, which is the 600 amp fuse at B1, and then we move left until intersecting the gray line. And then this is where this example here, I guess, it shows moving back down to intersecting with the x-axis at point D1, which corresponds to a let-through current of 8 Ka. So that is actually letting through an RMS fault current, an RMS current of 8 Ka. So that 600 amp fuse, when subjected to an RMS fault of 100 Ka, would actually limit the let-through value to only 8 Ka. So the third curve we want to discuss is the total clearing I squared T correction factor curve. So let's start with a bit of background information again. I squared T is a way to measure the thermal energy created by electrical current. It is quite commonly used when discussing fuse performance. When a fuse is operating or clearing a circuit under a high short circuit overcurrent condition, the amount of energy let through the circuit is referred to as the total clearing I squared T. The total clearing I squared T is the sum of two values, the melting I squared T and the arcing I squared T. The melting I squared T is the amount of energy required to cause the fusible elements to melt and separate. The arcing I squared T is the amount of energy let through the system from the time the fusible elements melt until the current flow has stopped and the circuit is completely opened. Again, the sum of the melting I squared T and arcing I squared T equals the total clearing I squared T. The total clearing I squared T value that is typically published on a product's data sheet is given at the fuse's rated voltage. But the total clearing I squared T is voltage dependent. Which means that the clearing I squared T for a product varies by system voltage, but it's only usually published at the product's rated voltage. So for voltages lower than the rated voltage, the total clearing I squared T can be determined using an I squared T correction factor curve. So we can walk through an example here to illustrate that. So in this curve, let's see what the total clearing I squared T value of the Littelfuse L70QS 125 fuse when used in a 500 volt AC application. So the L70QS 125 is a 700 volt AC rated 125 amp fuse. So the total clearing I squared T published on the data sheet would be given for 700 volts AC. But this application voltage is only 500 volts, so we're interested in what it would actually be at 500 versus the published value at 700. So the rated voltage total clearing I squared T value from the data sheet is 8795. And so we can locate at point A, which is at 500 volts AC, which is the application voltage, move up until intersecting the curve at point B, and then move over to the y-axis at point C. And we can see that the corresponding correction factor value is 0.55. So that value is to be multiplied by the published total clearing I squared T value at rated voltage. So 8795 times 0.55 is 4837 amp squared seconds. So what this is saying is you can anticipate, even though the fuse is rated for 700 volts AC, if you use it at a 500 volt AC application, you can actually estimate the total clearing I squared T to be a value less than what is published on the data sheet, and that value in this case would be 4837 compared to 8795. So another important characteristic curve we need to review is the temperature rerating curve. And this curve is quite important. It's one of the most commonly used curves for high-speed and general purpose fuses. This curve would be published or should be made available for nearly all industrial fuses, period. The current carrying capacity of a fuse depends on the operating ambient temperature of the application where it is being used. The current carrying capacity is reduced as the ambient temperature rises and vice versa. The temperature rerating curve can be used to determine this change in current carrying capacity across the entire operating temperature range of the fuse. Temperature rerating curves are specific to fuse types and are based on the ambient air temperature that is immediately surrounding the fuse, generally within a few inches of it. If the fuse is mounted in an enclosed fuse holder, then the ambient temperature is considered to be the air temp immediately surrounding the fuse holder, not necessarily the air immediately surrounding the fuse inside the holder. Temperature rerating curves typically have a wide range of ambient air temperatures on the x-axis and the corresponding rerating factor to be applied to the rated current of the fuse on the y-axis. So let's walk through a common example here So we're going to look at the current carrying capacity, or try to determine the current carrying capacity of this 30 amp fuse at 70 C. So the fuse rating is 30 amps, which is the current carrying capacity at ambient temperature. So we want to know the current carrying capacity at 70 C in elevated ambient. So point A1 is at 70 C on the x-axis, and we move up to intersecting the curve, move over to the y-axis, and we find the re-rating factor as 20%. This is an elevated ambient, so it actually will decrease the current carrying capacity. So this is a derating factor per se of negative 20%. So the current carrying capacity at 70 C would be the rated current plus the re-rating factor multiplied by the rated current. So 30 amps plus a minus 20% times 30 is 30 amps minus 6, 24 amps. So at this elevated ambient condition of 70 C, we should expect this 30 amp fuse to actually only have a rated or a current carrying capacity of 24 amps. And this, as you can imagine, is quite important. If that 30 amp fuse is assumed to be carrying, to be able to carry 27, 28 amps, that is true at a standard ambient temperature of, say, 25 C. But when using it at 70 C, over time and without that much time, this fuse will open because it should be taken that the current carrying capacity is only 24 amps. So next up is the peak arc voltage curve. When the bridges of a fusible element start to melt and separate during an overcurrent fault condition, arcing occurs inside the fuse. The arc produced inside the fuse continues carrying the fault current until it is extinguished by the fuse's filler material, which is usually some form of silica sand for most industrial fuses. During the arcing process, a combination of the inductive energy in the system and the fuse quickly shutting off the current causes a peak instantaneous arc voltage to appear across the fuse terminals that is often greater than the system voltage. This arc voltage generated inside the high-speed fuse, which again is higher than the nominal system voltage, can also appear across power semiconductor devices that are connected downstream of the fuse as an instantaneous reverse voltage. So care should be taken during the fuse selection process to ensure that the peak arc voltage from the fuse is less than the power semiconductor device peak inverse voltage to avoid a breakdown in the semiconductor device. The peak arc voltage correlates to the system voltage. So many high-speed fuse users need to understand what the peak arc voltage would be if a fuse was applied at a voltage less than its rated voltage. And that's where this peak arc voltage curve can be helpful. So this curve is a little bit different than the correction factor curves. In order to have a correction factor be useful, you have to have a published value at some level that correlates to the correction factor of 1. So in this case, oftentimes a peak arc voltage is not published as an absolute value. So this curve works a little bit different. It's not a correction factor curve. It more so correlates what the peak arc voltage would be, correlating to the operating voltage, so the system operating voltage. So here, let's walk through a quick example. So let's look for the peak arc voltage of a 400 amp, 700 volt AC fuse in a 500 volt AC application. So for example, it's a Littelfuse L70QS400 product. It's just 400 amps, 700 volts AC. The application voltage, 500 volts AC. So that would be point A on the x-axis at 500 volts. And we move up until we intersect with the green line that correlates to the fuse rating in question. So in this case, we're looking at 400 amps, which is the lower of the two green lines. Then we move over left to the y-axis until we intersect at point C. And that ends up being about 950 volts AC. So what this is saying is this fuse, when applied at 500 volts AC application, when it will open, actually it could have an arc voltage across it of 950 volts. So the the customer would want to be sure that their semiconductor devices can handle a inverse voltage of 950 volts. So the final performance characteristic curve I want to touch on is the Watts loss correction curve. Again, this is back to being a correction curve, so it'll be a factor that is based off some published value. At a high level, a fuse acts as a passive resistor under normal operation. It conducts current and generates heat. This heat generation consumes energy in the system. The amount of energy consumed by a fuse during its normal operation is referred to as a power dissipation or Watts loss. Global standards require fuse manufacturers to publish a product's Watts loss when tested at 100% of the rated current of the fuse. And this data for each fuse can be found in its data sheet normally. So nearly all high-speed fuses will have a Watts loss value published. However, in real applications, high-speed fuses are not to be loaded at 100% of their rated current. Instead, they're usually loaded anywhere from 60 to 80% of the rated current, depending on the application parameters. So it is often useful to know what the actual Watts loss value would be at an applied current that is less than the fuse's rated current. This is why the Watts loss correction curve is helpful. It too can be found in the product's data sheet. This curve will allow a user to estimate the expected Watts loss value at any current level between 30 and 100% of the rated current. So let's step through a final example and practice using this curve. So let's say we're looking for the Watts loss value of an L70QS125 fuse when loaded at 70% rated current, which is a pretty normal level to load this 125 amp fuse at. So the fuse rating is 125 amps, and again, per global standards, the Watts loss value at 100% should be published on the data sheet. So for this product, it is 24 watts. However, we're applying this fuse at 70% rated current, not at 100%. So at point A, we find point A at 70% on the x-axis, move up until we intersect with the green line, move over to the y-axis, and at point C, and the corresponding correction factor is 0.39. And that is to be multiplied by the published Watts loss value of the fuse at 100% of its rated current. So 24 watts times 0.39 is 9.36 watts. So that's just an example of, and it makes sense, if you put less current through a fuse, it will generate less heat and dissipate less energy from the system. All right, so before moving on to the next section, I'd like to give a real quick recap of what we just covered. High-speed fuses are applied in a wider range of applications than traditional fuses. Traditional fuses often have a very specific purpose, not all, but some, or most rather. So therefore, high-speed fuses, their data sheets include a lot of detailed information, including key performance characteristic curves that are necessary for properly specifying high-speed fuses for many applications. When interpreted properly, these curves can help users select the optimal fuse for protecting their semiconductor device in their own application. And again, these 6 most common curves are time current curve, peak let-through curve, total clearing I²T correction factor curve, temperature re-rating curve, peak arc voltage curve, and Watts loss factor curve. And using a combination of these curves will allow a user to better understand the fuse's specific performance within their own application. Now, I would like to briefly review the key parameters for fuse selection that can help narrow down potential fuse options for your application. Voltage rating. This should be probably the most most obvious but most important selection parameter. Obviously, the rated voltage of the fuse needs to be equal to or greater than the system voltage. Ampere rating. The rated current of the fuse selected should be greater than the system RMS load current. So it's important to note the RMS load current. Many loads for semiconductor fuses have varying loads, cyclic loads in some fashion. So the RMS portion of this is quite important to calculate it, and then use that value to estimate what your fuse rating would be. And a note here is that it's common that a fuse rated current sizing should be a minimum of a 125% of the load current. So let's say you have some cyclic load and the RMS calculation ends up being about 100 amps for the load current. You would want to use a fuse rated at a minimum of 125 amps for that. This is a kind of a standard go-to sizing factor. Our high-speed application guide, which I think there's a link later on in this presentation, has many other factors that can be taken into account to come up with a more specific sizing factor for your application. This is kind of generic when few application details are known. Interrupt rating. So the interrupt rating of the fuse selected should be greater than the max available system fault current. The max available system fault current is often known or can be estimated. And for example, if you have a fuse in a power converter or a motor drive, for example, in a factory, the available system fault current at that location of the fuse has many things impacting it. The size or the rating of the transformer feed, the distance from the transformer, the size of the conductors, all play a role, the transformer impedance, all play a role into what that available system fault current would be. So typically that can be known or estimated by the electrical engineer or system engineer that's coming up with the whole system architecture. Total clearing I squared T. We talked about this a little bit earlier, but the total clearing I squared T for the fuse, it should always be made sure that it would be less than the explosion I squared T of a semiconductor device. And again, that's the total clearing I squared T at the operating voltage, not necessarily at the fuse's rated voltage. And so to come up with what that total clearing I squared T would be at your system voltage, you would want to use that total clearing I squared T correction factor curve. So using that curve, estimate what the clearing I squared T would be and ensure it's less than the explosion I squared T of the semiconductor device. Peak arc voltage. So the arc voltage of the fuse selected, again, similar to the clearing I squared T, we want to consider this at the operating voltage, not at rated voltage. Should be less than the semiconductor device's peak inverse or reverse breakdown voltage. So it's again using the peak arc voltage curve to estimate what that would be at your system operating voltage, and then ensuring it's less than the semiconductor device's reverse breakdown voltage. Not doing so, you would risk insulation breakdown or a punch through of the semiconductor materials inside the device. So we just covered 5 general selection parameters, and this slide summarizes those 5 key parameters that can be used to help identify potential fuse solutions for protecting your semiconductor device. They are high-level parameters that can help filter out many of the fuse options that exist in the market. There are many, many options out there, but once you identify a fuse that meets these key parameters, then a deeper dive into the application can begin. So this can be kind of used, these parameters can be used as a filter for narrowing down your search for the proper solution. Once you have something that meets these 5, you can do a deeper dive, which is usually covered in a applications guide, which, as I mentioned, there's a link to it later on in this presentation. But at that point, other application parameters should be considered, such as ambient temperature, cyclic load currents, cooling systems, conductor size, system frequency, regenerative loads, and more details regarding these parameters and how they impact the fuse selection can be found in the HighSpeed Fuse applications guide. So with that, I'd like to thank you for your time and attention and turn it back over to Brandon to wrap up today's discussion before we have the open Q&A at the end.
Thanks, Ray. So with that being said, I'd like to discuss some of the resources and design tools that Littelfuse has available online and documents that have been created for your use. The first is our go-to central page, which would be littelfuse.com/Powerspeed. The Powerspeed has to do with our high-speed offering in terms of the different products we offer, and that would have the following information on this link. So it would be technical information that we'll get into, data sheets, ordering information, and drawings / images. And in terms of our design tools, we feel like we have a very comprehensive data sheet compared to competitors that offers extensive DC data. So our data sheet is, it's a one-stop, document, which includes TC curves, data information, I²T curves, all the curves that Ray discussed, along with all of the technical information that you need when looking at these products. Some additional tools in terms of the data sheet would be one document that we refer to today, which is our Powerspeed technical guide. So it's a deeper dive in terms of these fuses and goes into more of the considerations for the factors in terms of how would the temperature or other factors really affect from a mathematical standpoint on selecting a high-speed fuse, and also just a deeper dive than kind of some of the topics that we have discussed today. In addition to that, we have our high-speed fuse catalog specifically, which is available online, and some other selling tools we have is a cross-reference, which helps you when looking at a competitor in terms of the product name, how it refers to what the product category or how the competitor, let's say a busman or immersement fuse, and how that would cross-reference to our fuses. Last would be our Powerspeed Fuse overview guide. So it's a good short document that just includes hey, these are where high-speed fuses are used, these are the common applications, and this is the main purpose of a high-speed fuse. With that being said, I'd like to conclude our presentation and open the floor up for Q&A. Thank you.
Excellent. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. So for our first question, does a fuse need a current 0 during the arcing interval to interrupt the current to the load?
That's a good question. So I guess for having a current 0 would be for AC applications. Obviously, DC applications do not have a current 0. So to answer the question, a fuse does not require a current 0. However, if it is an AC rated only product, then yes, it would. If it's a DC rated product, then no. Generally speaking, though, a fuse does not require that. The current 0 crossing is very helpful for a fuse to clear a circuit. That's why DC ratings on fuses are much more challenging. And oftentimes, not always, but if you see, for example, a 600 volt AC rated fuse, it's not usually rated for the same voltage level for DC. It certainly can be, some are, but usually there are special design considerations to get the DC voltage rating up that high. So I guess to answer the question, it depends, but in theory, a fuse does not need it, but when there's no zero crossing, it is a big challenge.
All right. When there is a short-term non-sinusoidal spike in current, is calculating the I2T and ensuring the result is less than the pre-arcing rating a valid method to determine if the fuse will open?
Yes. So the answer, to answer that, I guess, that's absolutely what you want to do with some margin. So if you have some non-sinusoidal spike in current, calculate the I2T of that pulse, is what I would call it, and ensure that it is less than the pre-arcing or melting I2T of the fuse. In theory, ensures the fuse will not open. There should be some margin there, obviously, between those two values. And also, it depends on how often that fuse will see that pulse. So if that's a one-time pulse, it's one thing. If it occurs every 30 minutes, it's another story. And those types of details are addressed in the high-speed application guide. But yes, in theory, that is what you would want to do to ensure it's less than the melting I2T.
Okay. Fuses can be subjected to current pulses of a short duration. Low melting value, but high enough to damage the silver elements over time. How do you mitigate this effect in high-speed fuses?
It's another good question. So really for mitigating it in high-speed fuse, it really comes down to the element design. So it was mentioned here the silver elements, and yes, oftentimes high-speed fuses do use silver elements, which have a better performance than other materials such as copper. But it really comes down to the element weak point designs, the length, width, thickness of those weak points, how spread apart they are, and what you can do to have those thermal stresses have a minimal effect on the fused element. But really, again, that takes into account the sizing of the fuse. So you have current pulses of short duration with melting value high, but not enough to open the fuse. That would come into, similar to the previous question, I guess. You want to ensure that the I2T in those pulses is much less than the melting I2T of the fuse if it sees it very often, which if it occurs over time, then you need to put enough of a design margin or a margin factor in there when selecting the rating of the fuse. And again, some of those details are covered in the high-speed application guide.
Okay. Could you address the importance of LR time constant for DC applications?
It's very important. So the LR time constant is something very key. And when you're looking at DC application and a fuse has a DC rating, the DC rating usually comes with a specific L/R value. So, for example, Littelfuse has a PSR series products. It's rated for DC, and it is rated at a 10 millisecond time constant. And that's drastically different than a fuse rated at the same voltage but only 1 millisecond time constant, for example. So the L/R time constant is directly related to the amount of inductance in the system, and the inductance creates challenges for the fuse to clear a circuit during the arcing phase. The combination of more inductance causes a higher arc voltage, but also more inductance has more energy that's kind of pushing through the fuse when the fuse is trying to quench the arc and clear the circuit. So it is key, and you need to be careful to note what the L/R value is for a DC fuse. and make sure that it aligns with your application.
In what conditions is the I2T rating applicable? For example, should it only be calculated for current above normal or nominal?
Not all currents above nominal. So, for example, if you have a 100 amp fuse and it is subjected to an overload, let's say it's a full range fuse, it's subjected to an overload of 200 amps. That's, that fuse is going to take a long time to open, probably minutes, at only 200%. And the amount of I squared T or energy created there, I squared times, a few minutes, that's a big value. It's going to be much higher than the published I squared T values of the fuse. Those published I squared T values usually correlate to the short circuit region where the fuse melts fast enough to where there's not enough time for the fuse to dissipate any of that heat that's generated. Essentially, all the heat generated by the current goes towards opening the fuse and none of it gets dissipated. So really the I squared T rating is only applicable when the fuse is in a short circuit region. So, at a high level, maybe 10 times rated current and above. So for that 100 amp fuse at 1,000 amps and over is where it'd be more applicable than anything over nominal.
What performance characteristic distinguishes a standard fuse from a high-speed fuse of equal ratings? And if you could potentially provide some examples there. And also physically, how is this accomplished?
So for equal ratings, voltage and current, simply put, the high-speed fuse will be faster acting. So for the same level of overload or short circuit, the high-speed fuse will operate at a faster speed, be more current limiting than a traditional or standard fuse, as you call it. So there are several things that allow the fuse to do that. One is element geometry. Another is the material filler. But the biggest reason is that most very fast-acting high-speed fuses are partial range, and they're only meant to operate in the short circuit region. And by doing that, you can make the elements quite thin and respond very quickly for short circuits because you can generate a little more heat at low overloads because the fuse is not protecting in that range. So again, it's mostly filler material, and element geometry is really physically how that's accomplished.
Okay, referring to the TCC, does unsafe mean that the fuse will not break the current, or does it mean that the fuse may explode?
It means that the fuse may explode. So in the unsafe operating region, there are times that the fuse may not open because it is to the left of the TCC. But if it did open, which it could, depending on how close it was to TCC, it would potentially not open safely. And in the presentation, as mentioned, could have a catastrophic failure. It's a keynote, it's could. Not all result in catastrophic failures, but the fact that you could have one implies that it could be a dangerous situation. So care should be taken to not put a fuse in that scenario.
How are the peak let-through current graphs interpreted? Does it mean that the actual short circuit or fault current will be lower than the expected fault current?
My apologies. Can you repeat that real quick?
Okay. How are the peak let-through current graphs interpreted? And the second question was, does it mean the actual short circuit / fault current will be lower than the expected fault current?
Yes, that is exactly what it means. So again, if you have a 100 kA available fault current, you're having a fuse in the circuit could reduce that 100 kA fault current, depending on the fuse rating, anywhere from a few thousand amps up to 30 or 40,000 amps. The higher the rating of the fuse, the more let-through current we'll have. But yes, that's absolutely what it means. The actual let-through current level will be less than the potential or the available fault current level.
All right. When using the TCC curves, do we use the actual fault current or the let-through current?
The actual fault current. That question comes up. Most times we talk about this, and the TCC would be the actual fault current because the TCC was generated using actual fault current testing. So, for example, if you find on TCC, if you're looking for the melting time at 20 kA, 20,000 amp fault current, the test would have been at 20,000 amps. It would have let through something less, but that melting time is what would have been recorded on the TCC. So it is the available, not the actual let through.
Excellent. Well, I'm afraid we've run out of time. If you asked a question that was not answered, we'll be in contact with you soon to answer all your questions. This concludes today's presentation. On behalf of Electronic Design, I'd like to thank TTI and Littelfuse for sponsoring today's event, and of course, to all of you for joining us. Have a great rest of the day.